Hello and welcome everyone. This is the first lecture of our second week where we're getting into talking about observations and the data behind how we understand climatology and the climate systems that exist on Earth. Um, Fun fact for the day today, another map by my buddy Brian that was produced just I think on January 2nd or 3rd. He's pretty fast at this. He actually calculated the change in daily temperature variability, right? So remember we were talking about the 30-year time periods and how that shifted, and in class you kind of worked with the shift from the 60s, the time period 1960 to 1990, and then 1970 to 2000 and 1980 to 2010. This is the brand new 1990s through 2020. And what he's done is he's compared that to the previous 1981 to 2010 time period, the climatology for that time period that where we've been making all of our measures of change. And he interpolated this across all of these data points, and it's actually related to the topic that we're going to talk about today. But you can see a lot of these changes up here. I mean, we're talking like a 2 to 3% in parts of the Arctic, and at least a 1% change for most of Alaska. You have a 2 to 3% and even above 3% there in Idaho, which is fascinating. That's sort of the magic and treasure values, Boise and Twin Falls and whatnot. And so that's a really fascinating change, a 3% or 4% increase in temperature, change in variability in temperature. So that's not just an increase, but also, across the whole range, right? But it's fascinating to see just how much changed, right? It's incredible. I'm sorry, I was reading that wrong. This is less variability, right? So we're getting tighter in our distribution versus the orange and the yellow are kind of more variability. And remember, the take home yesterday or last week was that we generally don't see a significant change in variability. But let's talk about that a little bit more as we get into this. So we're talking about observations of data, like how do we know things are changing, or how do we even begin to start to characterize climate? Where does that data come from, and how is it measured? And we think of it in these four big buckets. I'm not going to go into great depth into why each of these are good metrics, because we're going to talk about that a lot over the next few weeks, where we do a chapter a week on each of these, basically. But today we're going to just talk about atmosphere and cryosphere, and then for the next lecture we'll talk about ocean and carbon and how we measure. And just remember, this is the conceptual understanding of climate. We have all these interactions, and so when we're breaking it up into these four things, we're kind of saying, okay, generally we think of the atmospheric inputs and how do we measure that, and then we think about the cryosphere and how do we measure the cryosphere, the frozen earth or the frozen ice on earth kind of piece, including sea ice and everything. So let's get into that. First off, the book kind of recommend going out and checking out these departures from normal again. And we talked about these anomalies a little bit last week, but realize that there's a difference between it didn't circle between land and ocean. And so we're going to focus for atmospheric observations on land. So there's obviously there's more to the atmosphere than just the surface of Earth. There's a lot of layers, right, in the atmosphere, and we're going to go into that a lot more in a week or two. But the most common proxy or common metric for observations of the atmosphere is surface temperature, and there's a lot of reasons for it. But first and foremost is that it's the most spatially contiguous, i.e., we can actually measure it on a spatial resolution that makes sense and captures the variability. And if you want an example of this, I mean, think about how would you measure atmospheric temperature in the three dimensions, right? So not just in the latitude, longitude, but also in the elevation of the atmosphere. Remember, it goes up 4 kilometers, 10 kilometers. You can imagine how hard that would be to have observations in those stratospheric and layers of the atmosphere, right? So we tend to focus in on surface temperature, and there's good papers, linking obviously everything that happens elsewhere in the atmosphere to surface temperature. So that's our proxy. The other reason that we include it or use it as our most common one is simply because we've been measuring surface temperature for a long time, and therefore we can extrapolate these longer term trends, which is really, really important. So, to realize that we've got global land temperature. Remember this anomaly thing where pre 1940 we really had, and then compared to the whole average for the entire time period, 1880 to 2020. It was much cooler back then, and since about 1980, we have not had a below the average global land temperature, which is saying an awful lot, right? So this captures that 30-year time period. So before, remember, we were starting with the 60s through sort of the 90s. So this was our climatology for a while. You can imagine how that plays out then when we go to the 70s to the 2000 and then the 80s to 2010. And now we are 1990 through 2020. And so our baseline has shifted. This is reflected in terms of the ranking of anomalies, right? So the most departure from that norm is then ranked on that NOAA website that the book kind of mentioned, and you can go check it out. 2016, still the warmest. This didn't include 2020 data yet, so we'll see where it comes in. But I don't think it's going to oust any of the top 2 or 3. But you can just see how much of a departure from that 140-year average, 2016, 15, 17. And it's no surprise, right? To most of us, you have all heard this. All of the hottest years have been in the last 10 to 20 years. And so this just kind of validates, and it shows you where, how much warmer it really was. I mean, look, 2015, 16, or 15, 17, 19 were all just as hot or above the normal. So remember that climatology is all about stats, and we're really interested in these trends. And so you can see this increase, right? And so this is, again, focusing just on the land, and there's a stronger signal in the land temperatures. That's due to a lot of the factors we're going to discuss later, but you can imagine, as we mentioned last week, water acts as a buffer. Therefore, it's less less sensitive to these changes, and so it can absorb a certain amount of radiation and energy, and therefore smoothing out sort of the peaks and troughs. So you get a stronger signal on the land, and it equates globally in land surface that we're increasing about 0.12 degrees centigrade per decade, right? So let's talk about how these observations kind of come to be. So we've got these graphs that we have all seen some element of, and most of it comes from these types of models. So they're models in the statistical sense, not in necessarily the computational sense. We're not plugging in mechanisms. We're not trying to explain these variations. We're simply taking data points and extrapolating. So here's 3 from the book that he mentioned, and just want to kind of highlight these, and you can go and check them out. You can read about these reconstructions, but it's really important to kind of realize that this is different than the global circulation models that you see in all the the sort of the, for lack of a better word, the doomsday forecasts, right? This is simply looking at the past. And it looks similar to the global warming kind of maps that we see, the ones that are forecasting changes, because it's built on this assumption that we, or this, not an assumption, but this practice of putting it into these grids, these boxes, right? Those of you who are taking GIS know what I'm talking about, but grids are basically think of them as Excel boxes, right? A cell in each Excel table. If you put that in a spatial framework, like across the globe, you can assign values. And what they do is they take averages of all the stations that happen to fall within those grid cells. But the reason we have 3 different ones is simply because we have, millions of weather stations that we could potentially tie into. And depending on which ones you look at, what criteria you have for sort of representativeness, right? Like if you chose only stations, like in the case of this one, mostly marine stations. Um, well, it's ocean marine stations. I don't know actually why why it looks so different. There's simply no data for most of the world. They've got it sort of here in the Atlantic, and they've got it across North America, or at least the United States and Mexico. But depending on what kind of criteria, right? Are you representative of the entire globe's surface? Are you looking at just land? Or are you looking at just ocean? Are you interested more in marine versus not? Are you interested in high mountains, or are you trying to exclude those? What kind of trend are you trying to pick up? Are you trying to get the just the deserts or in the forests, or what kind of trend? So there's all these decisions that you make on, okay, what stations meet the criteria that I'm most interested in understanding, and modeling statistically. All right, so we've got a whole bunch of options here, and you can read it. I think the book kind of mentions sort of how, or just some of these resources where you can go and check out. I mean, you can actually literally just download this data set. This is the Berkeley data set, I think, where you can go and you can see where the stations are that they use, the weather stations they use, how long those have been in operation, and what they had to do, whether or not they moved and whatnot, versus this is another data set, obviously a lot more comprehensive, and this is even a more comprehensive data set. And what a lot of climatologists have been doing over the past years is trying to figure out how do you statistically uh, include, or how do you include without creating statistical fallacies, um, these stations that maybe have only contributed 10, 15, 20 years of observations. Because if you think about it, the thinking about observing climate or weather for 140 years, well, that's only going to exist in a few select places, right? I mean, you think about, I mean, there wasn't even televisions 60 years ago in most of the world, right? So why would there be a weather station collecting data? But that doesn't mean that we can't use other types or it doesn't mean we can't use their data if they've only been collecting it for 40 or 50 years. It just means that you have to be really careful about how you treat that in comparison to a data set that goes back 140 years. And so that's been a lot of the efforts. I think this is one of the more earlier versions of gridded temperatures, and it's sort of, increased in sophistication and what they allow, what they include and what they don't include. There is no right answer. I can just anticipate some of you saying, "Well, which one do you trust? Which one do you believe?" There is no right answer, right? It really does depend on the nature of your question. If you're interested in just global surface temperatures, that's a very different question than are you interested in ocean and surface land surface temperatures, or if you're just interested in ocean temperatures. So you have to be really selective, and this is what climatologists are really good about, is understanding which networks of stations are the most robust for answering different types of questions, and then plugging it into these models where they then try to interpolate. So interpolate means if you've got 5 different stations down here in South Africa, right? How do you and say one station has an average temperature of 30 degrees centigrade and the other station has 20 and another has 25 and another has 20? How do you treat all those stations? Do you just take the straight average, or do you say, oh well, the one that measures 30 is in the low valley and the one that measures 20 degrees centigrade is up in the mountain? And okay, so we have to kind of adjust, we interpolate based on the fact that we know that air cools as you move up a mountain, and you get a more appropriate approximation of temperature in that grid cell. That's what we mean by interpolation. So, but this raises the question about, like, okay, what are the issues with these stations then? And there's some pretty well-known ones, right? This is stuff that I hate to say it, but climate denialists like to jump on these things all the time. So I figured we could spend some time talking about this. The first and foremost is changes in station location, and this is often the case. So most stations, at least in the United States, are located at airports. Well, if anybody's lived in a big city long enough, you know that airports move, especially because we seem to totally lack foresight and, actually build airports away from downtown centers, right? So I grew up in Denver, outside of Denver, and we had Stapleton Airport for many, many, many years. And if you go there now, Stapleton is completely surrounded by the megalopolis of Denver. I mean, it is completely surrounded. And so eventually, I mean, when I was I guess, going into high school, they built DIA, the Denver International Airport, and that is way out in the boonies. I mean, it's like an hour from the original Stapleton Airport. So if you think about the difference, an hour's drive makes in temperature, well, that's big, right? So that station, the official Denver's weather station, changed locations. Now Stapleton Airport is actually a redevelopment. It's really cool. Those of you taking land use planning are going to learn all about this. It's a really cool story about redevelopment. They're not monitoring weather there anymore. I'm sorry. So they moved the station, and that raises this question about, well, what happens when you move the station? There's also issues in instrumentation and data coverage. So you notice from the previous map that there's not always, data for certain grids, so certain places on the Earth. And we'll get into that in a little bit. And then finally, change in instrumentation, right? A lot of people like to point out, oh, our ability to measure temperature precisely was not the same in 1880 as it is now. Absolutely true. Absolutely true. Luckily, we have statistics and we can figure out what that error is. And we can estimate then, is the trend we're seeing greater than the error that we expect? And we can simply account for it. So let's talk about like changes in station location. It's, these are the stations used most commonly. This GHCN is one of the more widely used global networks for temperature data, or for weather data that feeds into these climate analyses. And you can see there's some serious bias, right, in the instrumentation data coverage. In the US, we have a ton. We like our weather. We are fascinated by it. We want to know everything. We want, it's not just good enough to have one in Ashland. You go to Weather Underground and we've got like 40, because people are just fascinated, right? And not to say that all those little cheapo ones that report to Weather Underground are actually used in this analysis, but it's indicative of just how interested we are. Same for where people live in Australia: Perth, Melbourne, Sydney, Brisbane. That's where 90% of Australia lives, and they've got good instrumentations. The Outback, not so much. Most of Europe, it's not bad. It's, this is a cartography kind of issue. I think they've got decent coverage, but boy, you look out in Russia and China and India, it's like, that's not great. That's not due necessarily to lack of instrumentation. That's also due to political, they don't want to share stuff with us. But of course, Africa, where there's low population density, of course, in the Amazon, and of course, in Canada and Alaska, there's just not the data coverage. Putting that aside, this is the trend, right? And what they did, this is one of the analysis to kind of get at whether or not the changes in station location makes a difference in detecting trends in temperature. And I mean, the take home is no, it doesn't. You can adjust it based on the location, and you can use laws of probability to test out then what's the potential increase or decrease if you move the site one direction here or there. And you can use some of these more modern weather stations then to kind of validate that, right? And then back forecast that. So you think about the 40 stations that we have here in Ashland. If they're interested in understanding the effects of, I think we moved our weather station in Ashland from downtown to the sewage treatment plant sometime in the 80s or 90s. That was the official Ashland weather site. But there's some complaints about that because the sewage treatment plant is right there on Bear Creek River, and so the winds and everything and the evaporative kind of loss went through the roof all of a sudden compared to the previous climatology. And so, with that in mind, they did these models of like, well, what happens when you move it in urban neighborhoods, rural neighborhoods? If you look at just one trend in urban versus the trend in rural, is that different than the overall adjusted average? And you can see that there's a little bit difference in magnitude, which is interesting. I mean, the reason that urban is slightly larger is because of that urban heat island effect, and that tremendously changes a lot of the climate that we end up seeing. But you see the exact same signal. You see that exact same kind of pattern emerging, and so that was one attempt at it. There's another where NOAA developed this global land surface data bank, which is their ability, or their best attempt at so far to reconcile what I was talking about, where we know there's a lot of stations with just 10, 20, 30 years of data, but that does not mean that it should be excluded. And so likewise, we can actually use some of the stations in Europe that have been going on for almost 300 years, because we can statistically account for how it behaves in relation to newer stations. And so this is a really cool one. And what they did here was they adjust all of it based on that number of years, and using some really cool statistical methods to test out that variability. And then they modeled the raw versus adjusted. So raw means taking the temperature data as it sits, and adjusted means when you put it into this generalized model, this interpolated model, what is the major difference? Because that's been a big complaint of the climate denialists as well, is that how dare you sort of take these spatially weighted averages and put them into these trends, because then you're losing the true signal. Well, this pretty well proves that that's not the case. Those spatial averages just make it a lot more statistically robust, and so you take those adjusted values, and that's what most climatologists utilize. And then there's this assessment of variability, and whether or not we're becoming more variable. There's been a lot of discussion in the literature about, is climate change, or is climate changing in its variability? Are we less predictable now? And there's valid arguments on both sides for sure. I'm sure you've all heard that with warming comes more extreme events. And extreme events do play into variability, although not tremendously. So in this analysis, they're trying to get at, so in an average, kind of what we were looking at last week in class, an average day, so in Ashland, right, the temperature changes from 30 degrees to 60 degrees, let's say, something like that, right? Even if the baseline shifts and no longer are we getting down to 30 as the low, we're getting to 35 and we're going up to 65. That's a shift in the baseline, but it's not a shift in the variability, right? It's not this major shift in, we're still getting out of 30 and we're getting up to now 65 or 70. We're not increasing the width of this bump, right? So what they did is they mapped this out, the distribution of variability. You can see a bit of this baseline shift, right? So this is the 50s to 70s, 70s to 80s. We see this shift towards the higher temperature anomalies. It was once normally distributed. Now we're skewed, right, a little bit. And what it did is adjusts for that skew just to measure the width of the humps, the bumps in the distribution. And they found that there's actually very, very, very little. So a slight increase or a slight decrease in standard deviation after 1980, a slight increase in standard deviation in 1980, meaning some stations are increasing standard deviation. Remember, is a measure of that variability right there. So if you have an increase in standard deviation, this widens out. If you have a decrease, it gets skinnier, becomes a little bit more peaky. So we're seeing both, kind of, right? Which makes good sense, and we'll talk a lot about what that means. But this shifting baseline is key, really. This kind of shows that shift. This is that New York Times article that gets referenced in the book. It's pretty remarkable, right? That we're seeing this significant change in our baseline temperatures. Cool, huh? But what happens when we don't have data? Well, this is interesting. So this is a project that I'm working on right now with a colleague at University of Nevada, Reno, and because we both worked up in Alaska previously. So she worked for the Scenario Network of Arctic and Alaska Planning as a climatologist, and now she's the state climatologist for Nevada. But we still have our feet firmly planted in Alaska and Alaska issues, and she's very much interested in sort of well, all kinds of things climatological in Alaska. But what both of us came together to do was figure out, because I'm big into the mapping and understanding where we know stuff and where we don't know stuff. And so we came together to say, well, what is the station coverage look like for Alaska? And where's the most optimal places to put new stations so that we can learn better about Alaska's climatology? Because as you can see from this, I mean, we have decent coverage right along here. Like that's our best network. And anybody that knows anything about Alaska, that's because that's the Alaska Canada Highway coming in and up to Tok and Glen Allen and everything, and coming down the Parks Highway, which is, Denali's in here. Fairbanks is up here, and so this is the road that connects Anchorage to Fairbanks, and there's Denali and everything. So it's the roads. That's where we have roads. Everywhere else, we have to take an airplane or a helicopter to. So the density is not great, which means we have large gaps in our understanding. So we're actually developing this whole survey to reach out to folks using climate data and most importantly, the folks that actually set up these stations. These are Park Service, USGS, those kind of federal agencies, to say, hey, which stations do you use? Which stations do you not use? Because we want to know which stations they don't use because they know of data issues or whatever. Because stations go out, and if you have to take an airplane to it, sometimes they're out for 6 months, and if it does that 3 or 4 times over a 10-year period, not to use that station. It's just not reliable anymore. And so we're really trying to get a good understanding of what's the reliable stations, which ones they use the most often, which ones they don't, and then where, if they had a bunch of money where they could put an extra 10 stations, where's the most optimal spot. And we're coupling this with some pretty cool models that she's done to kind of test out the uncertainty associated with these gaps. So you can, again, use a lot of statistics to kind of figure out if we only know stuff about these three things, these three areas for this part of Alaska, what happens if we all of a sudden find a 10-degree shift? Is there any evidence elsewhere that could possibly be, if we're trying to interpolate just between those things? And so she's done some really cool uncertainty maps, and that it's coupled with that as well. So this is still very much a real issue, right? We're still trying to fill in some of these gaps, and this is still in the United States, where we have the best funded science, well, at least traditionally the best funded science in the world. And so you can imagine in other parts of the world, there's still very much big gaps in our coverage. The other thing that we're trying to reconcile here is just how many different networks there are for measuring temperature. I mean, this is, none of these mean anything to you all, right? But that just gives you a sense of, these are all groups that independently work and have different missions and all kinds of things than each other. So this just gives you a sense of like how complicated it is to A, find the data, B, have good representation, and then C, really could make good sense of it. So the other way that we're measuring atmospheric, surface temperatures is satellites. So I know there's a couple folks that have taken remote sensing with me, but and maps and cartography. And so you may remember that almost all of our satellite platforms have a sensor for measuring surface temperature. And this is true for Landsat all the way down to 30 meters. It's or up to AVHRR and the 1 and 4 kilometer kind of stuff. But we actually measure land surface temperature based on the signal that we get in satellites as well. So this is yet another way of measuring surface temperature that's a lot less sensitive to all those station location errors. The flip side is that, you know, most of these are captured at the 1 and 2 kind of kilometer grid cells, meaning, you know, it's one pixel from the satellite perspective, 1 pixel for all of Ashland. And we know that climate can vary pretty tremendously, or at least weather can vary pretty tremendously, depending on where you are in Ashland. If you're down at Bear Creek or if you're up in on the TID, those are very different weathers, right? Weather system or weather temperature feelings and precipitation and everything, right? So the flip side of satellite, you know, while you don't suffer from lack of coverage because we're taking it from space, although it does get messed up in the Arctic sometimes because of clouds, um, it you know, it has that continuous coverage, but it doesn't have necessarily that spatial resolution that's important for, you know, say urban planning and that sort of thing. But this is pretty cool. This is July surface temperature in the daytime. So this, and I think this was from 1990. So, but it's just a single snapshot, right? Single day, or no, I think it was a monthly average. But nonetheless, you know, a single year monthly average. So it's not a trend or anything. It's just straight surface temperatures, and that's what it looks like at night. Isn't that fascinating? And so that's one of the cool things we can do with satellites is, you know, temperature, taking pictures day and night, regardless. And stations can do this as well, but this is a lot more contiguous. And since a lot of stations are solar powered, you know, we're running into this with our SOU weather station right now, where it's solar powered. So during the day, it's getting a strong enough signal. But some nights, I mean, if depending on the previous day, some nights it's getting cold enough, it's draining that battery. And so it's nice to have these satellites taking temperature readings as well. Okay, so that's the basics of atmospheric observations and sort of the data that we use to make these trends and measure those anomalies I was showing you. Let's talk about the cryosphere. So I don't know how many people think about the cryosphere or even recognize that as a major part outside of maybe your Earth Sciences 101 kind of classes. But the cryosphere, as we'll learn more and more throughout this class, is a pretty major driver of climate, and we understand this. It's also a really, really, really effective way at measuring the changes in climate because it's just so obvious. You know, we can't see temperature, but we can see melting. We can see glaciers disappearing and ice caps disappearing. And so let's talk about that a little bit, right? So this is one of this out of the book showing sort of the U.S. Well, this is where we've seen the most change in the North Pole, the Arctic sea ice is right here. So this is the average extent in the 1980s, which is pretty awesome. So each of these lines kind of represent an extent from the 1980s, and then in 2010, this is what it looked like, and it's pretty amazing, right? So, and if you're not used to looking at polar projections, polar maps, this is Alaska. So this is that north slope of Alaska, the Arctic coastal plain that I was talking about earlier in the first week. This is the Seward Peninsula. Bering Land Bridge is right here. So this is Russia, right? In Siberia. And this is Sweden, Norway, Finland over here. So you can see most of the ice is being lost in the Beaufort and Chukchi seas. That's what these two seas are right here, and it's amazing. It's just a tremendous change. I love this animation that NOAA generated for us, kind of showing that extent both as a map, but also as a graph. So this is the minimum sea ice. So this is at the peak of summer, right? Because any given winter, you have the potential of rebuilding that ice, and so and sometimes all the way back to the previous extent or some norm, right? But it's this minimum that we're most interested in because that does represent. I mean, if you get past a certain threshold, you simply can't rebuild the previous extent of ice, and that's unfortunately, I think, what we're seeing right about here. This is called one of those potential tipping points where we've lost enough mass that it's hard for sea ice to rebuild because sea ice builds off of existing sea ice. And so that's one thing that scientists are kind of observing or considering and modeling is whether or not we crossed a threshold there. Only time will tell, right? But I love that animation. So we can do this spatially again using satellites. We're measuring the spatial extent of sea ice in the Arctic. And I like this too because it kind of gives this nice just simple map of this is the median sea ice edge in over the last climatology kind of period, and this is sort of the extent as of December of 2020. So this is rebuilding stage, right? But what I also want to say is that we map out, we can measure the concentration of sea ice as well. And this is huge because while you can rebuild sort of the previous extent, if you've lost half of the mass under the surface of this, which is what we're seeing along here in Canada and along Greenland and Europe and all throughout Alaska. I mean, this is just super, super thin now ice compared to what it used to be. So we measured not only extent, but we measure the concentration. And we do this not only just for the poles, but we do this for inland glaciers, right? So this is the Muir Glacier that the book talks about, and it's significant, right? And then we can do this. We did this for Kenai. And what we did was we looked at Skilac Lake, which is just, so Kenai is there south of Anchorage. You're going to see a lot from there. I apologize. It's just where I've done a lot of work. And we looked at these aerial photographs. We actually did this really cool GIS project involving undergrad students where we took old photos. This is from 1950s that the Army flew, and we georeferenced them to the Earth, and then we draped it over in Google Earth, and then we put it into a planetarium. It was so cool, and we flew around and everything. And we built this little slider, and I just wanted to show this little slider to you, and it's hyperlinked there on the slide. But you can actually do this nice little comparison of this is what it was in 1950. This is what it was in 2013, I believe. Yep, 1952 to 2013. So there, the glaciers all the way down into the lake. You can see rivers coming off of it, and it retreated all the way back up. It's still touching the lake, but now we largely have this nice big lake. It's fascinating. So that's in a 60-year time period, that amount of loss. It's not insignificant. And we see this pretty well across at least the northern hemisphere when it comes to inland glaciers. This is another paper by a colleague of mine, Shad O'Neill, looking at sort of the mass balance. So not just extent again, but the actual volume of ice associated with these two different glaciers. And you see, similar trends. Wolverine Glacier is just north of Kenai, the one I was just showing you. So this is kind of a numerical representation of that loss. Golconda is up in the interior of Alaska, and it's a lot more precipitous decline in mass balance. And we see, like I said, this across the globe, primarily in the northern hemisphere. So in the southern hemisphere, there's not a ton of glaciers. Think Chile, Argentina, even New Zealand, those kind of places. There's not as much landmass. There's not as much glaciers down there, and their interannual variability. So the variation in glacial, coverage and weight between years is just as much as the interannual variability. Well, the decadal. So anytime you kind of have that, it bounces up and down enough from one year to the next over the decadal variability. If it's the same amount of variation, say 20 or 30 square kilometers, then we say that it's not strong enough signal, and it could be from just random noise. But this isn't the case in the northern hemisphere. Pretty much across the board, we see significant declines, and even in some parts of the southern hemisphere, we still see a decline. We've got the southern Andes here, where we're seeing some. So it's this is just another way that we're measuring sort of the change in the cryosphere. And the last one I would just talk about. So while the glaciers aren't showing as strong as a signal in the southern hemisphere, Antarctica is. So I focused a lot on the Arctic. When I kind of think about Antarctica too, and specifically the ice mass, because the extent has not changed a tremendous amount. Although we all have read about those big, icebergs coming off that are sometimes the size of Rhode Island. The extent is not as strong a signal as the actual loss of mass. And that's what this graph is showing. It's from that climatenasa.gov place. But then they generated this video that just shows, again, that the extent is not necessarily changing a ton, but man, the mass is. So you'll start to see these red areas grow and increase as time goes on. And that's the thinning of sea ice and the thinning of cover of ice there. It's kind of amazing. And so this is based off of GRACE. And the book mentions GRACE, and I encourage you to read about it if this is of interest to you, because GRACE is a satellite platform, just like the ones that take our pictures, except it does it in tandem. It's a twin satellite system. So what they do is they point at the same place on Earth, but they're spaced out a specified distance. And what they're doing is measuring absolute heights so that they can measure the change in gravity. And from the change in gravity, so if you assume certain things like plate tectonics aren't moving on a daily or monthly basis, and you think about the other things that might influence gravity, like volcanoes or whatever, if you assume that those are relatively constant over a 30-day period, any changes in gravity then are due to changes in either ocean density or in sea ice. And so this is what the GRACE mission does: is it measures gravitational forces on the Earth, and it extrapolates then how that plays out in terms of loss of sea ice. And this is then validated by going out in the field and dropping a core down here and saying, oh yeah, gosh, it really is much, much thinner now. Same for Greenland, same pattern that they've observed. This is again using GRACE, and they've produced this nice little visual. But what we see in Greenland is a lot more in the extent and a lot more in the mass loss. I mean, significant loss in the mass of Greenland. And hopefully you've heard about this too, is just that tremendous. I mean, it's I can't remember the actual value. Oh, it's 280 gigatons per year of ice lost on average over the last decade or so. I guess 2 decades. So this is a pretty serious observation, a pretty sobering observation. So this tells us that things are warming, right? Basic laws of thermodynamics say that if ice melts, it's because it's warm, and if it doesn't reform, then that means that it's warmer year round. And if you see that year after year after year after year, you can infer, especially when you cross-reference it to our temperature data, that yes, truly things are getting warmer. And that's the take home, right? So in the atmospheric side, we have weather station data, and that when you extrapolate that over long time periods, you get your climate observations. There is bias in location, density of location stations, gridded interpolations, and accuracy. But there's conceptual, i.e. like physics-based models, as well as statistical ways to remove those errors and get good estimations of temperature, annually or monthly or even on a day by day. And because of this, because of these records, we've seen a shift in the baseline and a significant trend in warming. On the cryosphere side, Yeah, we are largely relying on satellites. It's pretty hard to measure sea ice balance across a broad geography without satellites, and so we use it both from imagery and as well as these gravity measurements and sea ice extent as well as mass is measured, so that we truly understand, how much ice is contributing. And remember, the book talks about how much Greenland and Antarctic melting is contributing to things like sea level rise, which we're going to talk a lot about the next one. And how do we know that's happening? And the interannual variability is easily measured compared to the annual variability, so that you understand, is it true change, is it not true change? And this is why we know it's mostly the inland glaciers in the northern hemisphere that we see this. And then, yeah, Greenland, Antarctica, and northern hemispheres are just way down. We've lost, in some places 40, 50, even 60% of the ice that we had just before, 1950. And that has a tremendous impact on our climate system. It's both a result of our climate system, but is also, as we'll learn in the second half of the term, a major forcing in our climate system. And we'll talk about that more next time.